Hello. In the previous video, we studied several examples of systems of linear equations. We showed two methods how to solve them. The first method using eliminations in variables. The second method was elimination in the matrix form. We didn't name any methods like that before, and today we study Gaussian elimination and Gauss-Jordan elimination method. Okay. Let's consider the following example. X minus 4y plus 3z equal to 5. Negative x plus 3y minus z equal to negative 3. And 2x minus 4z equal to 6. We don't have any y in the third equation, so we just move, right? Just leave this as blank, okay? Right here. All right. So let me rewrite this in the matrix form, okay? I will pick coefficients from each equation. In the first equation, I have 1, negative 4, 3, and 5. In the second, I have negative 1, 3, negative 1, and negative 3. 2, 0 right here because we don't have y, negative 4, and 6. So this is the matrix form of the original system. Last time we already, solved something like that, okay? And let me repeat the main idea, right? The main idea is you pick the first equation, you solve for x or y or z, whatever you want. But in this case, yeah, let's choose x, right? You solve for the x and you plug that into the second and the third. So you just eliminate the x in the second and the third equations. And you get some system, again, of three variables. But in the next step, we just forget about the first equation, right? We need to handle the system in two variables. And then once we solve that system, we substitute that back to the first one. And we can find the x. That is the main idea, okay? And on the matrix form, yes, you have 1 right here. You have to eliminate all terms in here. You need to make them equal 0. Agree? And then once you finish with that entry, you move to the next one right here and maybe sometimes right here, right? If you have more than 3 equations. All right? So let's give this a name, right? Such form of matrices is called augmented matrix. Augmented. Or sometimes they say, yeah, that is extended matrix. Why extended? If you pay attention on this form, the first part of this matrix is this guy. Is that correct? Let's denote this by 8. Okay, so I can write that is AX equal to B, where B is 5, negative 3, and 6. So we know about this equation already, right? At very first lecture of this course. So this is the matrix form of a system linear equation. The matrix A is called the coefficient matrix. The coefficient matrix. Because in the matrix A, we have all coefficients of x and y and z. You see that? Let's look at this one more time, okay? What you can see in the first row has all coefficients of variables in the first equation. 1, negative 4, and 3. The second row, you have negative 1, 3, negative 1, negative 1, 3, negative 1. 2, 0, negative 4, 2, 0, negative 4. You see that? That's why A is called the coefficient matrix. Okay? And of course, if you look at A from another point of view, like from the column point of view, okay? So what is the first column? The first column has all coefficients of the x right here. You see that? So you have -1, -1, and 2. The second column contains all coefficients of y. You see this? -4, 3, and 0. And then the last column is 3, -1, -4. Those are coefficients of the z right here. Okay, so that's why sometimes say the first column is for the x, the second is corresponding to the y, the last one is corresponding to the z, and of course, it depends on the system, right? How many variables you have. Then the number of variables should be the number of columns. Don't forget that. So the number of columns in the coefficient matrix is the number of variables. The number of rows in the coefficient matrix is the number of equations. Okay, so you have coefficient matrix in here and augmented matrix in here or extended matrix in here. Extended or augmented matrix has one more column. That is the free variables. It's right here. Does that make sense? So this is about the names of matrices in this system. Okay, now let's solve this. So I will eliminate all x. So I have 1 in here. I keep the first equation or the first row, and I multiply the first row. I just add the first row to the second because you have 1 and -1 right here. You see that? Just add them. So you got 0, and then you get -1, you get 2, you get 2 right here. And for the second, for 2 right here, I just multiply the first row with -2 and add to the third. Okay, add to the third. And let me rewrite this. Just row 1 plus row 2 and add to row 2. So I have 0 in here. -4 with -2 is -8. You see this guy, -8. So add 1 is just 8. Sorry. And 3 with -2 is -6. -6 minus 4 is -10. And then 5 with -2 is -10 plus 6 is -4. That's what I have. So I already eliminate, right, all terms in here. So I got 0. Now we can move to this term, right, to this term. And we have -1, we have 8 right here. Again, I want to eliminate this guy, okay? So I multiply the second row with 8 and then add to the third row. Okay, so I don't do anything with the first row. I keep that 1, -4, 3, and 5, 0, -1, 2, and 2 right here. 0, I have 0 right here. 8 with 2 is 16, minus 10 is 6. 2 with 8 is 16, minus 4 is 12. Okay, so now we have the form right here. It's interesting form, right? It's interesting form, you see. Such form is called echelon form. You see, echelon form looks like echelon form, right? Okay, so if you start from the very first matrix right here, you use some operations we call elementary operation. And finally, you got the echelon form of that. So, of course, this form is much simpler than the original one, right? Okay, let's talk about these elementary operations. What did you do? You do some operation like this. you add one row, you add one row to another row, right? So you don't change anything. So I can write in here, I can list all of them, okay? So I add multiple of a row to another. So we don't change anything. You see, this is multiple of R1 add to the third, right? Or multiple of R1 add to the second means, in this case, just multiply by 1. We don't change the system. We have an equivalent system. Don't forget that. And the next operation, you might interchange equations. Of course, you interchange equations. You don't change the system. So you have the same system, okay? The same means the solution sets are the same. And the next one, you multiply a row by a constant. Okay, multiply a row by a constant or divide a row by a constant. That is the same. Look at this. Now you get this guy. We'll show that right here. You have 6, 12. Usually in the previous lecture, we rewrite that like 6z equal to 12, right? And then you solve for the z. You get 12 divided by 6, that is 2. But we can do that right on the matrix by dividing the third equation by 6. You see that? Because our purpose is to get 1 in here, right? Because the coefficient 1, you see, the coefficient 1 would be z. You see that? So that's why that is about multiply a row by a constant or divide a row by a constant. So all these three operations are called elementary operations, and they will not change your system in the sense that if you got a new system, the solution set of the new system should be the same as the solution set of the previous system. And if you go back to the original, so you have equivalent systems. Okay, you have equivalent systems. Of linear equation. Okay, so let me solve this to the end. I will divide the third row by 6. I will get the following one. 194, 3, and 5, 0. 91, 2, and 2, 0, 0. 1 and 2. So from the third equation, I already saw that actually z is equal to 2. You see, z is equal to 2. All right, this is what we did last time. That's what we did last time. And this method is called Gaussian elimination. It's called Gaussian elimination because we eliminate, right, all terms in here. So like, from the first equation you pick one entry, sometimes we call it is the leading entry, and then you make all entries below that become 0 because you want to eliminate, right? Once you finish with this, you move to the second one, the second entry in here. This is the leading element, right? The leading entry on the second equation in the echelon form of this, right? So, and then you make this guy become 0. You see, this is right here in this step. And then you move to the next one until you got an echelon form of the matrix. And then you can solve for the last one, right? You go back, you solve this equation, you go back to the second equation, you go back to the first equation. So that means you do back substitution. Okay? And that method again is called Gaussian elimination. Last time we did that, but we didn't name it. Right now, I will show you another one. We don't have to do back substitution in variables. I want to do back substitution right in here on the matrix. How about that? on the matrix. And then at the end, I will show you actually it is much easier, right? It's much easier and clearer. Okay, how to do that? Now, I'll do a backward. I will start from this entry. Okay, I want to eliminate all z in the first and in the second equation. You see that? When we start Gauss elimination method, we pick some entries in here, right? For the x, and then we want to eliminate x in the second and the third equations, and so on. Now we have the z right here, and I don't want to see z in the second and in the first, because we already know z, right? So I will eliminate z in the first and the second equation. We do almost the same thing. We have 1 right here. This is 2. In order to make this guy disappear, I just multiply the third row by -2, add to the second. Does that make sense? And of course, that will not affect all this term because we already have 0 right here. You see? It's very good. So let me write that. I multiply the third row by -2, add to the second row, okay? And then I get, so I start from the last equation. It is 2. And here is 0. Here is -1. They will not change because we have 0 in here. Don't forget that. Here I got 0. 2 with -1. -2 is -2. Add to 2 is I have -2. Okay, and for the first guy, here is 3, right? I multiply the second row by -3. I write here the third row by -3. Add to the first row, okay? I got 1 in here, -4 in here. Here should be 0. -2 with -2 with -3 is -6, plus 5 is -1. Okay. Alright, so we finished this guy. Alright, we finished with this guy. You see? This make this guy 0. Here you have 1. You just need to eliminate all these guys. So you make them 0. Now we already finished with this. We move to this guy. Because we go backward. You see this? Alright, so I have -1 here, I have -4. No problem. I multiply the second row by -4, right? And I add to the first row. So I got, here's 1. Okay, let me write these 2 rows, so because we don't do anything with them. 0, 0, 1, and 2. And here I got 0, right? Here should be 0. -2 with -4 is 8. 8 plus 1 is 7. Okay, so from here you already see the solution. It's very simple form, right? It's very simple form. So this form is called reduced row echelon form of the original matrix. What does it mean reduce? If you have this part only, you have row echelon form. But if you reduce everything in here, right? So this is reduced. And from here, you can see the solution. You rewrite the first equation. So what is the first equation in this case? That is just x equal to 7. You see that? The second is y equal to 2. I just ignore negative in here. I mean, multiply the second row by -1, right? You got this. The last one is z equal to 2. And this is your solution. Alright? So this method, if you just continue Gaussian elimination, right? In another direction. So you got a reduced row echelon form. And that method is called Gauss-Jordan elimination. It is just the name. If you do one way, you have Gauss elimination. If you do another way, 2 ways, you got Gauss-Jordan elimination. Alright? So let's repeat again, right? Gaussian elimination helps you to find the echelon form, but Gauss-Jordan elimination helps you to find the reduced row echelon form, and from there you can find the solution of the original system. All right, we have x1 minus x2 plus 2x3 equal to 4, x1 plus x3 without x2 equal to 6, 2x1 minus 3x2 plus 5x3 equal to 4, and 3x1 plus 2x2 minus x3 equal to 4. In this case, you have 4 equations in 3 variables. Okay, so let's write the augmented matrix of this system, or the extended matrix. I just need to pick coefficients, right? Okay, it has 2 parts. The first part, okay, the second part is 4, 6. That is easiest one, so I just collect 3 coefficients, and then I write the coefficient matrix in here. Okay, the first row I have 1, negative 1 and 2. The second row 1, 0 and 1. The next row is 2, negative 3 and 5, and then the last row is 3, 2 and negative 1. You see, and the coefficient matrix has 4 rows and 3 columns. 4 rows is corresponding to 4 equations, 3 columns is corresponding to 3 variables. Okay, all right, now let's use Gauss elimination or Gauss-Jordan eliminations. Okay, we have leading element in here, which is 1. That is good. We don't have to change, right, the equations. So I will eliminate all these 3 guys. I will make them become 0. Okay, let me write in here. So I need to multiply the first row by negative 1, add to the second row, right? That is the first thing. And then I multiply the first row by negative 2, add to the third row, multiply the first row by negative 3, add to the fourth row. You see that? So we do all operations at the same time. Okay, so I fix the first row in here. Here is 4. This is 0. Negative 1 I got 1. Negative 1 I got negative 1. Negative 1 I got 2. Right? Negative 4 plus 6 is 2. Move to the next row. I got 0 in here. Negative 1 with negative 2 is 2. Minus 3 is negative 1. Negative 2 times negative 2 is negative 4. Plus 5 is 1. Negative 2 with the 4 is negative 8. With 4 is negative 4. Then move to the next one. 0 in here. Negative 3 with negative 1 is 3. Plus 2 is 5. Negative 3 with 2 is negative 6. It's negative 6 minus 1 is negative 7, right? And then negative 3 with 4 is negative 12. Plus 1 is negative 11. Okay. Now, let's move to the next leading element. I have the next leading element is right here, which is 1. Okay, I will eliminate these 2 guys. I make them disappear. So I will do the following one. I multiply the second row with the 1, just that, right? Add to the third. Oh, it's pretty easy. Okay, and then I multiply with the second row by negative 5, right? And add to the fourth. Okay, so I have 1 in here, negative 1, 2, and 4. I have 0, 1, negative 1, and 2, 0. I got 0. I got 0 in here, and I got negative 2. Interesting. And here I got 0, I got 0 in here. Negative 5 is, I have negative 2 in here, okay? And then in here I have negative 5 is negative 10. I have negative 21. Interesting. Okay, so I'm done with this element. Now you see 0, 0, 0, but I want the echelon form, right? So I can interchange two rows in here. I interchange them. I will get 1, negative 1, 2, and 4, 0, 1, negative 1, and 2, 0, 0, negative 2, negative 21, 0, 0, 0, and negative 2. Now I already have the row echelon form. You see that? This is the row echelon form. What can I see in this form? If you compare this form with the previous examples right here, this one. Okay, let me copy this, right, and then put them together, and then you see it better. I copy this and I will just, okay. So look at this. In this example, we have this form, okay? If you count the number of non-zero rows, in this you get 3, right? Okay, so what 3 is the number of non-zero rows in the coefficient matrix and in the augmented matrix. I write here in the coefficient matrix and in the augmented matrix. So you have 3 equal to 3. You see that? In the coefficient matrix right here, 3 non-zero rows. And in the augmented matrix, you also have 3 non-zeros. But in this example, what is the number of non-zero rows in the coefficient matrix? You have 1, 2, and 3. The last row is already 0 in the coefficient matrix. So you got 3 in here. What is the number of non-zero rows in the augmented matrix? In this example, you have 4. 3 less than 4. Okay? All right, look at this. If I continue solving this system, right? Let's pay attention on the last one. Because, you know, when we got a row echelon form, we always need to start from the last one, right? So the last one looks like 0 equal to negative 2. Because on the left-hand side, you don't have anything, right? All coefficients are 0. So you got 0 equal to negative 2. No solution, of course. You can see this. Right? You can see this relation. For this guy, you have solution. You have solution. Of course, not now I don't want to say about the number of solutions, but I just want to say, yes. If you have something like this, the number of non-zero rows in the coefficient matrix less than the number of non-zero rows in the augmented matrix, in the row echelon form, right? Don't forget that, in the row echelon form, then the system does not have any solution. But if in the row echelon form, the number of non-zero rows in the coefficient and augmented matrix are equal, so you have solution. You know, that is very good criterion, right? To memorize. Because otherwise, you know, you start from this step, right? And then you want to go back. And oh my goodness, what is this? Yeah, of course, no solution. But, you know, right now you can say, yes, the number of non-zero rows in the coefficient matrix in here less than the number of non-zero rows in the augmented matrix, no solution, done. Okay, so in this example, we see that, yeah, actually the system does not have any solution. And the K factor is about the number of non-zero rows in the row echelon form. Okay, don't forget that. That is not about, the number of coefficients and equation in this case. If you see three variables in with the 4 or 5 and even 1 million of equations, that does not tell you anything about the number of solutions. Don't forget that. We need to get the row echelon form, or sometimes at least we need to know the row echelon form, right? And if you want to solve that to the end, and if the system has solution, so you need to get the reduced row echelon form. Okay, and only in that way you can see the solution of your system. All right, so I think we can finish the lecture today. In the next video, we will study more examples about the system of linear equations.